All right, so what's the goal? There's 17 problems, and I'm just going to work through them and talk about what to think about, you know. It's a little bit better than just seeing the solutions because we're going to see what's the thought process. Now, you might be wondering, okay, are these the problems that I need to know? I mean, do I only need to focus on these 17? In some sense, they're pretty good. If you take the final exam and you walk out and then you come back to these 17, you're like, oh, that one and that one and that one, they were all good. They all had something to do. So these are good problems. These were written after the final was written, so they were written with an informed viewpoint. That's not to say these are the only things you should study. We want you to study lots of things. So you'll see that there's some advice here. Two pieces of advice. One of them says, do hard problems. Now, hard here doesn't mean computational. We're not trying to get you to spend time practicing your algebra and arithmetic. We hope by this point you've already mastered your algebra and arithmetic. And if you haven't, Calc 3 is coming. More opportunities. So that's going to be good. So when we say hard, what do we mean? We mean problems that make you think. Because that's what we really want to see is how well have our students learned to think. And we hope the answer is pretty well. So that's what we're looking for. So look through the problems. If you get your problems like, I'm not sure how to do that one, that's a one to look at. Of course, you know somewhat about what topics will be on the exam, so that should help also narrow your search. The other piece of advice is to take care of your health. We have students who show up to final exams and they're so tired because they pulled an all-night review session, they end up falling asleep. It's a bold strategy and doesn't usually pay off very well. So get enough sleep. You know, get out from time to time, go out for a short walk, eat good food. When your body is healthy, it helps your mind to operate better. So that's the other piece of advice. And part of that, of course, is starting your studying early, which is what you're doing by being here. All right, well, with that said, let's begin. 17 to go. And number 1, find the integral, an antiderivative, x squared over 1 minus x squared to the 3/2. Oh, that was from a long time ago that we talked about these things. So let's see what's going on here. Well, I see here to the half, and when I see that, and especially when I see a square root involved, that suggests trig substitution. So trig substitution is our way of dealing with square roots. Now, what's the rules for trig substitution? There's 3 things we could encounter. So if we encounter something that looks like the square root of a number squared minus variable squared, well, that comes from the sign. So we should make a substitution involving sign. We'll write them all down just for reference. If it's a squared, number squared plus variable squared, the right substitution to make is tangent. And the last thing is if we see a square root of a variable squared minus a number squared, the right substitution to make is secant. Now, the reason we say the right substitution is the goal with trig substitution is to find a way to get rid of square roots. Because square roots have been a challenge for us for classes, you know, several classes. All right, well, we see in our case, because of this half here, that's the square root. And we see 1 minus x squared, which means we're in this setting here. So this is a trig substitution problem, which means the first thing to do is make the substitution. You got to identify what problem it is. Then you have to identify the right substitution to make, and away we go. Now, what do we need to do? Well, we need to make sure we update everything, including the dx. dx becomes cosine theta d theta. And then the other thing is, of course, to say, well, what is 1 minus x squared to the 1/2, or the square root of 1 minus x squared? Well, that's actually very deliberately something that's going to be nice, because it's going to come out from trig identities that this becomes our cosine. So, what do we have? Our integral, x squared over 1 minus x squared to the 3/2 dx, is going to become x, we replace, that's sine squared. Dx, we replace cosine. And theta d theta. Then 1 minus x squared to the 3/2. Well, that's cosine theta cubed. All right, so there's our substitution. Now we've transformed our problem from an algebra problem to a trigonometry problem. We say, okay, let's start seeing how to rewrite it. So we start looking for cancellations and functions to rewrite. In this case, we can cancel off one of the cosines. Then you have sine squared over cosine squared. Sine squared over cosine squared becomes tangent squared. All right, so we have to integrate tangent. And now we say, all right, well, how do you integrate tangent? Especially, how do you integrate tangent squared? And the answer is you don't. Tangent squared is not on our list. But we think about the things that are on our list. And when I say on our list, 10 basic integrals we can do. There's a nice thing on our list related to tangent squared, which is secant squared. So we know our identities. Of course, sine squared plus cosine squared equals 1. That one we know by heart. But there's a related one that says tangent squared plus 1 is secant squared. And we say, aha, this can become secant squared theta minus 1. And now we're in good shape. Because the integral of secant squared, that's tangent. And the integral of 1 is theta. So tangent theta minus theta and plus c. Now, it feels like we're done because we did the integral, but we're not done. Because we started with x. We can't end with theta. When it's an indefinite integral, we've got to make sure we go back all the way. So let's go back. So how do we do that? We come to our substitution. X is equal to sine theta. What does that tell us? It says if you were to draw a little triangle, put theta in the corner, then sine of theta is the opposite, which would put us x over the hypotenuse, and that means the last side, by Pythagorean theorem, is the square root of 1 minus x squared. You might say, ooh, we've seen that before. Not a coincidence. You should see that before, because that's what motivated our substitution. So, how does that help us? Well, now we have our triangle, and what do we do? Well, tangent of theta is opposite over adjacent, x over square root 1 minus x squared. Then I have theta. Well, for theta, again, we can come here. We can say that theta is arc sine x. So take the inverse sign. So x over square root 1 minus x squared minus arc sine of x and plus c. All right, well, good warm-up. Now, on a side note, just remember, if it's an indefinite integral, don't forget the plus c. That's a point. And you want to get all the points. That's your goal. Got to get them all. Okay. Next one. Evaluate the integral 1 to infinity arctangent of y over y squared plus 1 dy. Include any limits needed. Well, that's an interesting instruction, include any limits needed. So it makes us a little bit suspicious. Why would they give us this instruction? Well, upon closer examination, we see that this is not just any integral. There's a little bit something improper. We see that infinity right there. So this is an improper integral. So an improper integral is any integral that deals with infinity. Now, you can deal with infinity in many ways. So this is a case where the infinity is in the bounds. All right. So how do you deal with improper integrals? Well, the answer is you use limits. And it really says you got to use the limits. Oftentimes in practice we don't. But if it tells us you got to put the limits in, well, we're going to do it. All right. So let's see what we do. Well, one way you can do this is you can say, if I want to do the integral from 1 to infinity of arctangent of y over y squared plus 1, I can do this as a limit. So this is where limits come in. So if you see something that says include limits and there's an integral, it probably is some sort of an improper integral. And it's a limit as our bound goes to infinity. So I'm going from the integral 1 to c. Now the nice thing is once you take off the infinity, it's no longer improper. So that is to say that the piece inside of here, that's perfectly fine. No worries. So we do the integral. Now looking at this, we suspect it's probably not a hard integral. I mean, it's an arctangent. That means it's got to be lovely. And if we look a little bit closer, we say, aha, if I start with the arctangent of y, call that u, the derivative of arctangent is 1 over y squared plus 1. which means that that would be du. So on a little side note here, making the substitution, this would become the integral of u du. Well, that integral is a half u squared plus c. Put the u back in, half arctangent of y plus c squared. All right. So that tells us that our integral here is 1/2 arctangent of y squared, evaluated from 1 to c. Now, this is a big C, capital C, constant. This is a little c, limit as I go to infinity. I should have used different letters because my capital C's and my lowercase c's look very similar. This becomes the limit, as we head to infinity, of 1/2 arctangent of c squared minus 1/2 arctangent of 1 squared. All right, well, we're almost there. So let's see what happens. Well, arctangent of 1, we know that. That's pi fourths. So that's easy. And the only place where c shows up that we have to take the limit is in this arctangent of c. And so now the question is, well, what's true about arctangent? If you graph arctangent, what you'll see, it's tangent turned on its side. And so as you approach infinity, it approaches an asymptote. Well, which asymptote is it? Do you know? Anyone? Pi over 2, pi halves. Right. So that's the limit. This goes to pi over 2. So that says, okay, you can take this limit. So it's 1/2 pi over 2 squared minus 1/2 pi over 4 squared. And you could stop here because it doesn't say simplify. If you don't have to simplify, you don't need to. If you like to live dangerously, you can keep going. It's pi squared over 8 minus pi squared over 32, or 4 pi squared over 32 minus pi squared over 32, giving us 3 pi squared over 32. But like I said, if it doesn't say simplify, once you get your answer, you can stop. If it does say simplify, simplify. It's a good rule of thumb. Follow the instructions. In fact, it's great advice. Follow the instruction. So, another one. Okay, evaluate the integral 0 to infinity, square root of t in the denominator, e to the minus square root of t in the numerator, dt. Include any limits needed. Well, okay, we suspect it's improper. Yeah, of course it is, because we see the infinity. However, be careful. There are multiple reasons things can be improper. Now, in this case, you'll see there's something down here which can be 0. Now, in the previous one, if you went back to look at it, you'll see that the y squared plus 1, well, that can't be 0, so we didn't worry. But square root of t can. And in particular, you're going to run into a problem at 0. So you actually have two problems here. So what do? Well, if you have problems, then what you do is you break them into smaller problems. And, lessons for calculus, lessons for life. All right, so we're going to say, look, the integral 0 to infinity of e to the minus root t over root t dt, well, we'll just pick something between 0 and infinity. We go about halfway, say about 1. That's about halfway, I guess. E to the minus root t over root t dt, and plus 1 to infinity of e to the minus root t over root t dt. Now, it didn't have to be 1. You could have picked any number, but we like 1. 1 is a lovely number to work with. All right. So in this case, we have that there's a problem. So we're going to take a limit as we go to 0. Now, we can actually be more specific as we go to 0 from above. Integral a to 1 of e to the minus root t over root t dt. Now, why from above? Well, because I'm going from 0 to 1, so I'm on the positive side. I don't want to go from 0 from below because I can't take a square root of a negative number. And you might say, well, why didn't you specify it before when you had infinity? Well, look at infinity. How can you approach infinity? You can't approach it from above. You always approach it from below. So that's why I don't need to worry about the direction. 1 to b, e to the minus root t over root t dt. Well, let's do a little bit of side work here. finding the antiderivative of e to the minus root t over root t dt. Now looking at this, it's highly suggestive. And what do I mean by that? Well, if you stare at this, you'll see if I take this piece, because when you think about substitution, you should always, it's one of your first things to look at. If it's not on your list, there's not some silly, simple thing to do, substitution is always your first go-to idea. In this case, if you set u equal to minus root t, du would be minus 1/2 t to the minus 1/2, because this is, u is also minus t to the positive 1/2. 1/2 comes down, subtract 1. Or you get minus 1 over 2 root t. I forgot my dt's. Said another way, we can say that 1 over square root of t dt is minus 2 du. So, making the substitution, we'll have that this becomes the integral of e to the minus, oh, sorry, not minus, because I already put a minus here. So it's e to the u with a negative 2 du. Well, that's easy. That's just e to the u, or, so we end up with minus 2 e to the minus root t. So, has a nice antiderivative. All right, now back to our regularly scheduled problem. So this is the limit as a goes to 0, and we have minus 2 e to the minus root t evaluated from a to 1, plus the limit as b goes to infinity of minus 2 e to the minus root t evaluated from 1 to b. So what do we get? Well, over here we're going to get minus 2 e to the minus 1. Then minus minus makes plus 2 e to the minus square root of a. And, oops, I forgot to write my limit. Limit as a goes to 0. So there's my limit still. I haven't taken the limit yet, so I still have to keep writing it down. Limit as b goes to infinity, minus 2 e to the minus root b, and then minus minus makes plus 2 e to the minus 1. And at this point, we can start saying, all right, now we can take our limits. And we say, what happens? Well, these parts, the 2 e to the minus 1, so those are numbers. Nothing happens to those. So nothing to worry about. But on the other parts, we say, okay, a is going to 0. And we say, there's no problem here. It's just basically going to square root of 0, which means that this part goes to 2. On this part, well, we're getting square root of a large number, which is going to be large. Negative, okay, so it's a large negative number. E to a large negative number is very small, and this goes to 0. I should have said that goes to 2, and this is already minus 2 e to the minus 1, and this is 2 e to the minus 1. And now we're ready to simplify, and we see, lo and behold, what happens. The place where you cut will cancel out. That's what should happen. The 0 goes to 0, and here we're left with 2. Now, if any one piece had gone off to infinity, either one, then we're done. We don't have to do both. But if they both go to a finite number, in this case they were both finite, then we put them both together and get our final answer. All right, well, find the antiderivative of tangent to the fifth theta, secant squared theta, d theta, by making the substitution u equals tangent theta. Oh, they didn't even give us a choice. They told us what to do. All right, so this is an integral involving powers of tangents and secants. So in our case, what do we need? Well, we have u equals tangent of theta. Du would be secant squared theta d theta, because the derivative of tangent is secant squared. And that was great. It's right there. All right, so what do we get? Well, we have to write everything that's not going into our du as in terms of tangent. Well, it's already done. That's u to the fifth du. So integrate u to the fifth. You get 1/6 u to the 6. Don't forget your plus c. And that becomes 1/6 of, going back, tangent to the 6 theta plus c. Oh, that's good. Wow. I hope we get that one. That'll be an easy one. Well, maybe. Let's find the integral of tangent to the fifth theta, secant squared theta, by making the substitution u equals secant theta. Now you might object and say, wait a second, we just did this problem. But you look, it's a different substitution. So there's more than one substitution to make. Sort of the moral of this story is there's more than one choice. Of course, which one do you pick? The answer is whichever one is easy for you. All right, so we know our substitution for u. So we can say, all right, du, derivative of secant, that's secant theta, tangent theta, d theta. So, all right, so how do we do it? Well, we look at our integral and we say, let's pull off a secant theta, tangent theta. So I have to pull off a single tangent, so I'm now tangent to the fourth, and a single secant, so I'm in a single secant, times secant theta, tangent theta, d theta. So this part on the end becomes the du. And now we have to think about, well, how do we integrate the rest? To do that, we want to make sure everything's in terms of secant, because that's our substitution. So we say, all right, this part, great to go. That's going to be u. But the problem is that's not secant. But it's trig. And if there's one thing we know about trig, there's always an identity. And so in particular, if you're ever dealing with integrals involving secants and tangents, make sure you know how to work with them. And the key is the identity we had before, tangent squared plus 1 is secant squared. Or, if you like, tangent squared becomes secant squared minus 1. Now in our case, we need tangent to the fourth, so you square both sides. Tangent to the fourth theta is secant squared theta minus 1 squared. So this is what's going to happen here. Secant squared minus 1 quantity squared, which is going to become u squared minus 1 squared. So we get the integral of u squared minus 1 squared times u du. Now if you multiply u squared minus 1 out, expand it, that'll become u to the fourth, but there's another u, so u to the fifth, minus 2u squared, then again there's another u, minus 2u cubed, plus 1, and because of the u, plus u. And now we're ready. 1/6 u to the 6 minus 1/2 u to the fourth, because it's 2 over 4, plus 1/2 u squared plus c. And replace. So replace, remember we're doing secant, so 1/6 secant to the 6 theta minus 1/2 secant to the fourth theta plus 1/2 secant squared theta plus c. Good. And if you look, we can compare our answers and see, aha, they're not looking the same at all, but they are the same. And it's just a matter of manipulation. So don't worry. If things don't look the same, it's okay. It's possible to make different choices. Now, which choice should you make? Do the one that's best for you, the one that you understand, and the one that you can carry out. That's the best one. If you can't carry it out, don't do it. Do something else. All right. Well, those were integrals. Now it looks like we're into our next phase, applications. So find the volume which results from rotating the region 0 less than or equal to y, less than or equal to 2 secant squared x, for 0 less than or equal to x, less than or equal to pi over 4, around the line x equals half pi. Now, it wasn't marked here, but this is 1/4 pi here. So this is our region. I guess I'll call it R. So here's our region R, and we want to find the volume when we spin it around this line. So, we're going to end up with some sort of shape. All right. Now, how do we actually find this? To find this, we think about what we're going to rotate. Now, the way it's presented to us is as y is a function of x. So we're going to think about taking very small pieces. So I take a small piece and I'm going to spin it. And if I spin my small piece, I look at what shape I form. In this case, it's going to be a little tiny shell. So here we're going to be thinking shell method. Now you might say, how else would I know to do the shell method? Well, because we took off the washer method, that's a good clue. Don't do the washer method. Okay, so probably going to do the shell method. All right, So if we're doing the shell method, we've got to remember how the shell method works. So the shell method says, generically, you integrate from wherever you start to wherever you stop, or if you're really adding them up, you have a 2 pi, then you have a radius, and then you have a height. And finally on the end you have a little bit of thickness. So what these pieces are, is these are identifying how you find a shell. How do you find the volume of a shell? So when we talk about various things, they're actually fairly easy to identify. The thickness is really it's a bad word. We should say the thinness. This is our small bit of x. The height, well, that's from top to bottom. Now in our case, the bottom is 0, and the top is 2 secant squared x. It's a function. It could be the case that we have different functions on top and bottom, and if that's the case, just subtract. But in our case, that's what we have. Now the radius, that's how far you are away from where you spin. So in particular, that's this length here. So if I want to go from x to a half pi, and you always want to make sure you get the sign right, because, it would be silly to reach the end and say, oops, that's a negative number. What happened? Well, so how do you get the sign right? Well, you always take whichever one is larger, subtract whichever one is smaller. So pi halves is more to the right than x. So I'm rotating on the right-hand side. So it's pi halves minus x. So pi halves minus x. All right. And what about our start and stop? Well, that's also given to us. It's 0 and pi fourths. And I guess I should say 2 pi is 2 pi. That one's not too surprising. All right, so integrating 0 to pi fourths of pi halves minus x times 2 secant squared x dx. Now one of the things you can do is you can multiply this out. So it's 0 to pi fourths, 2 times pi halves becomes pi secant squared x, and I'll actually make this its own integral, minus integral 0 to pi fourths, we have 2x secant squared x dx. Now the first integral, let's just go ahead and get that out of the way. The antiderivative of secant squared, we know. So the antiderivative of secant squared is tangent. So tangent x from 0 to pi fourths. And if you plug in 0, you get 0. Great news. Plug in pi fourths. Tangent of pi fourths is 1.
Steve,
yes?
was your 2 pi out?
Ah. All right, there it is. All right. So, all right, 2 pi. Good. Plug in 0. Get 0 still. And then pi fourths. Tangent of pi fourths, 1 times 2 pi times pi. 2 pi squared. All right. So we have this second part. All right. Let's work on that down below. So we want to find the integral of what? Well, we're working on, I'll just do the integral 0 to pi fourths of 2x secant squared x dx. The bad news is that's not on our list. We don't know how to integrate that right away. Well, but we can work on it. We have the tools. We have the technology. So in particular, we look at this and say, 2x, I'd like to get rid of the x. And a good way to get rid of that x is if I could take a derivative. And say, all right, can you integrate secant squared? Oh, I can integrate secant squared. All right, so this is good. When you have one part you can integrate, and another part which you can differentiate, and it's going to make something simpler, well, that says we're setting ourselves up for integration by parts. So that's something to know. Now, not every problem is going to say this is an integration by parts problem, so you have to recognize it. So how do you recognize it? Look for two things multiplying together, and you say, I can't do them both together, but maybe I can do a little bit of one and a little bit of the other. All right. So in our case, we want to take the derivative of that, the 2x, and the antiderivative of the secant squared x dx. So I'm going to call this u and dv. So if u is 2x, du becomes 2 dx. And if dv is secant squared x, well, that means it's the antiderivative of secant squared, which we noted above, is tangent of x. Okay, so this becomes what? 2 times x times tangent of x, evaluate 0 to pi fourths, then minus the integral of v du. So minus 2 integral 0 to pi fourths, tangent of x dx. Now, if you don't like doing it with a definite integral, you can go ahead and do it with an indefinite integral, and just remember at the end, throw the bounds back in. All right, well, so that's good news. Here we can do the first one because you can evaluate it at 0. It's 2 times 0 times tangent of 0. That's extra 0, so that's good. Then you get 2 times pi fourths times tangent of pi fourths, which is pi halves. So this part here is going to be pi halves. Now, do we know the antiderivative of tangent? We haven't used it much, but we know it. Do you remember? There's a natural log of secant. Log secant, because if you take the derivative of log secant, it's 1 over secant. Derivative of secant is secant tangent. Secants cancel and you end up with tangent. It's on your list of 10 things. So it's good to know that. All right, so log secant, evaluate from 0 to pi fourths. So what do we get? Pi halves minus 2. Okay, secant of pi fourths. Well, secant of pi fourths is square root of 2. What's 1 over cosine of pi fourths? And cosine of pi fourths is 1 over root 2. And then subtract, well, secant of 0 is 1. So that's log of 1. But that's gone because log of 1 is 0. So we end up with pi halves minus 2 log root 2. Okay, well, now what do we do with that? That is this piece here. So we have the 2 pi squared, then we have the minus 2 pi times pi halves minus 2 log root 2. So let's see, what does that do? Well, you can imagine we multiply in, and so we still have the 2 pi squared from the first term, then minus 2 pi times pi halves minus pi squared. Minus 2 pi times minus 2 becomes plus 4 pi log of square root of 2. Well, 2 pi squared minus pi squared becomes pi squared. And if we wanted to, 2 to the square root of 2 is 2 to the 1/2. And there's a nice property about logs, just a little note here. Log of square root of 2 is log of 2 to the 1/2 is 1/2 log 2. So this gives 1/2 log 2 times 4 pi makes it 2 pi log 2. And boom, there you go. There you go. That's not so bad. That's a nice one in comparison. Okay. Find the volume which results from rotating the region 0 less than or equal to y, less than or equal to 2, square root of x to the fourth minus 16, for 2 less than or equal to x, less than or equal to square root of 5 around the y-axis. So this is a pretty tall region. In fact, this is actually scaled down vertically. It should be about twice as high as what you see here. So this is 2, and this is square root of 5. So it's like a toothpick or something. Now, how do we do this? Well, you can imagine what's going to happen here is you take a slice and you spin it around, and we're going to get shells again. Can't quite draw the picture because it's going to be off the screen. But okay, this is a shell method, and I go to shell because we are talking volume, so it's going to be something we learn how to do volume with, and so that's going to be shells. All right, well, how do we do this? Well, the formula, same formula that we had before. So the volume is going to be equal to the integral from our start to our stop, 2 to square root of 5, 2 pi, and then our next thing is our radius. Well, we're spinning around the y-axis, so that's at x equals 0. So the distance, high value minus low value, is x. And then we're going to have the height. Well, here the height is the function, and that function is 2 square root x to the fourth minus 16. And then our thickness, dx. So that's what we have to integrate. Now we start thinking about how do we integrate this thing? Well, certainly we see a square root, and one of the things when you see a square root and you see a sum or a difference, you're like, ooh, I should think of this as like a sum or a difference of squares. In particular, this looks like x squared squared minus 16. You say, okay, so that's kind of heading towards trig substitution. Maybe as an intermediate step, let's do the following. Let's suppose we call this x squared, we'll call this u. Then the 2x very conveniently turns out to be du. Well, that was very convenient. It's almost like they planned for that to happen. Okay, so suppose we do that. So what would this become? Well, if u is x squared, then to update our bounds, because these are x bounds, and we want to update everything. Whenever you make a substitution, always update everything. So instead of going from 2 to the square root of 5, we're going to go 2 squared. So that's 4 to the square root of 5 squared, which is 5. Okay, so that's our new bounds. 2 pi. The 2x dx becomes our du. And now the other part becomes the square root of u squared minus 16. All right, so now it's a little bit cleaner, a little bit simpler, and a little bit more clear about what's going on. This looks like a trig substitution problem. So we think about trig substitution, and we talked about it earlier. We said, well, if we're doing a trig substitution, we have to look at what's the right form. Now in this case, it's a variable squared minus number squared. So that's a secant substitution. In particular, the right substitution for us to make is u equals 4 secant theta. The 4 here comes because that's 16, 4 squared. So before it was just 1. That was why we didn't bother with putting a number in front. But now that there's a number, okay, we put it there because we want to make sure it simplifies nicely. So what does du become? Du, derivative of secant, is secant tangent d-theta. Now we have, of course, the great question, do we want to update our bounds or not? Well, sometimes I'm not a big fan of updating bounds here, but, well, let's do it without the bounds. So let's say, do this little side note, 2 pi square root of u squared minus 16. The reason I'm a little bit nervous about the bounds is because I don't really know how to handle arcsecant of 5/4. So I'll deal with that later. So if we don't worry about bounds, so we're just doing an indefinite integral, then this becomes 2 pi, and then we have du becomes 4 secant theta tangent theta d-theta. But what happened to that square root of u squared minus 16? Well, if you look at this, square root of u squared minus 16, that's going to become square root of 16 times secant squared theta minus 16, which is going to be square root of 16 times secant squared minus 1. And aha, great choice, because square root of 16 is 4, and the square root of secant squared minus 1 becomes the square root of tangent squared. Not a coincidence. It was chosen wisely. We chose well. So there's a 4 tangent theta. All right. So let's see. What do we have here? Aha. I did not choose well when I did this problem. So 16 pi integral of secant theta tangent squared theta d theta. All right. So how do you integrate secant squared times tangent squared? Now, it's not terrible. This becomes integral of 16 pi. You can replace tangent squared, similarly as we did before. You can say that tangent squared is secant squared minus 1. And then you get 16 pi and secant cubed minus secant. Now, the secant, that's one of our integrals we should know, but okay, we're going to do a 5-minute side note here. If you don't want to go on this 5-minute journey, it's okay. But here we go. if you're integrating powers of tangents and secants, so tangent to the nx, secant to the mx dx, there are certain things that make you happy. So what are the things that make you happy? If, if you can do the following, if m is even, you're happy. Because what you can do is that means you have a secant squared x available for you to pull out. Life is good. Life is good. Now, what else makes you happy? Well, if you have a secant x, tangent x, and everything else in terms of secant. So, what would that be? That would be if n is odd, I believe. You're also happy, because you can make a substitution. And the other case is you're very unhappy. Now, where are we? We're in the other case, because we have secant cubed. All right, so, refresher. How do you integrate secant cubed theta d theta? The answer is, do you remember? Normally we just give it to you, but I'm just kind of curious. Do you remember? This tells me I should have done the problems before time. All right, the way you do it is you do it by parts. Here, this is your dv, this is your u. du is secant theta, tangent theta. V is, antiderivative of secant squared is tangent. So, what do you get? You get uv, secant theta, tangent theta, minus the integral of v du. So that's secant theta, tangent squared theta d theta. All right, now, what is that? Well, if we work on this, so this becomes secant theta, tangent theta, and then tangent squared, you replace this by secant squared minus 1. So this becomes minus the integral of secant cubed theta plus the integral of secant theta. All right, well, so that's secant theta, tangent theta. We can integrate secant, that's log secant plus tangent. But then we have this last part, minus the integral of secant cubed. And you're like, but that's what we were trying to find. And this is our mwahaha. Yes, it was. We did it intentionally. All right. So what does a mwahaha mean? Well, it means you move this back across. So now you have 2 of what you're looking for is equal to secant theta, tangent theta, plus log of secant theta plus tangent theta, plus a constant, and now you divide by 2. So the integral of secant cubed is 1/2 secant theta, tangent theta, plus 1/2 log secant theta plus tangent theta, plus c. So that's the integral of secant cubed. You are not going to be expected to know that. I just want to be clear. But if you want, you can always derive it. You have the technology. Okay, so catching up to where we're at. So we got to this point. So we now know how to integrate secant cubed. It's here. 1/2 secant theta, tangent theta, plus 1/2 log secant theta plus tangent theta. But then we have to subtract the integral of secant. Well, the integral of secant is log secant plus tangent. And there we go. There's our antiderivative plus a c. Plus 1/2 minus 1 makes minus 1/2. There's a half here. So you end up with 8 pi times 1/2 secant theta tangent theta minus 1/2 log secant theta plus tangent theta and plus c. All right, now back into our normal problem mode.
Should it have been 32 pi and then it goes down to 16 pi?
Should what have been 32 pi? Oh yeah. 32 pi, 32 pi, 32, 16. right? And then the halves come out. Well, that's okay. I'd still get a sticker. You know, it's high enough. All right, we're close enough. Now, are we done? No, we're not. Well, that's the integral in terms of theta. We want to go back in terms of u. So, what's u? U is 4 secant theta. So, secant theta is u over 4. Well, what's tangent theta? Got to draw our triangle. So secant, that's going to be hypotenuse over your adjacent. So that means that the opposite side is going to be u squared minus 16. So this becomes 16 pi. This is more complicated than I expected, but that's okay. You should do hard problems. Hard problems. Ones that challenge you. U over 4, square root of u squared minus 16 minus log u over 4 plus square root of u squared minus 16. Okay, so there's our antiderivative. Now, what's left? Well, we're almost there. The only thing that's left is to evaluate.
Shouldn't tangent be square root of u squared minus 16 over 4?
Over 4, yes. Don't worry, I get better as I go on. So we're going to have 16 pi u over 4 square root of u squared minus 16 over 4 minus log of u over 4 plus square root of u squared minus 16 over 4. Evaluate that from 4 to 5. All right. Now you plug in 5. 16 pi. You get 5/4. Square root of 25 minus 16. 25 minus 16 is 9. Square root of 9 is 3. So 3/4 minus the log. And here we're going to get 5/4 plus 3/4. All right. That's what we get when we plug in 5. When we plug in 4, we're going to get 4 over 4. Square root of 16 minus 16 is 0 over 4. Gone. On the inside, 4 over 4, that's a u and that's a 4, which is 1. Square root of 16 minus 16 is 0 over 4. That's log of 1, which is 0. That's gone. So what do we have? We'll multiply the 16 through. You're going to get 15 pi, 3 times 5 times pi, minus 16 pi log 5/4 plus 3/4 is 8/4, which is 2. Okay. Well, let's not do that one again. All right. Good. On to some simpler problems. Easy stuff now. Use polar coordinates to find the area in the first quadrant that is inside the circle of radius 2, centered at the origin, and above the curve y equals 1 over x. So that's the picture. So we have this circle here of radius 2. So we can write this in terms of polar coordinates, r equals 2. And then we have this line here, y equals 1 over x. Now there's a slight disconnect here because y equals 1 over x is not in polar coordinates. So we can't just say, aha, I'm ready to go. We have to think a little bit. So let's think about what we're going to do. We should get this in terms of polar coordinates. Now a nicer way to write y equals 1 over x is the following. So y equals 1 over x, I can say that's x times y equals 1. And we replace x by what it is in terms of polar coordinates. R cosine theta times r sine theta equals 1. Now, at this stage, pulling out an r squared, I see cosine theta times sine theta. I usually like to write sine theta first. Sine theta times cosine theta. And one of the things that you try to think for or try to look for are ways to simplify. So one of the things that I see is that this is very reminiscent of an identity. So there's 6 identities that you need to know. We've mentioned 2 of them. Here's a couple of others. If you want cosine of 2 theta, that's cosine squared minus sine squared. If you want sine of 2 theta, that's 2 sine theta cosine theta. if you want power reduction, you might as well throw those in. Cosine squared is 1 plus cosine of twice your angle over 2, and sine squared is 1 minus cosine 2 theta over 2. Okay, so here, sine theta, cosine theta looks a lot like the double angle. So we can do that. We say, well, all we need to do is put a 2. So we'll put a 2. But of course, if you put a 2, you also need to divide by 2. So this can become r squared sine of 2 theta over 2 equals 1. All right, so that's almost the curve. It's certainly fairly clean. But if we want to write it in terms of r equals something, we would say r squared is 2 over sine of 2 theta, or if you like, you could say that r is the square root of 2 over sine of 2 theta. So that's our inner curve. All right. Well, good. So now we have our curves totally in terms of polar coordinates. The next thing to do is to figure out the right angles. Because when we're figuring out area, we need to say, where do we start our angle? Where do we stop? And of course, once we're going, we have to know the inner curve and the outer curve. So we have to figure out where these curves intersect. Well, where do they intersect? Well, it's actually not so hard to figure that out, because they intersect when what's true? Well, r has to be 2. So I can come down to any relationship here and just pick whichever one is easiest to work with. So for instance, if I take this relationship here and I plug in r equals 2, what do we get? We get 2 squared sine of 2 theta over 2 is equal to 1. Which says I need sine of 2 theta equal a half. So I'm looking for an angle where sine of that angle is equal to a half. That's going to be my input into sine. So how do you find that? Well, we've done trig before. We know our unit circle. So if you know your unit circle, the angle, or I should say the first angle where that happens, so that's the angle I want, is pi 6. So the first time you get sine of an angle is equal to a half is pi 6. Now, you might be nervous and say, do I need to fully memorize my unit circle? And I will tell you honestly right now, no. But it's good if you do, But if you don't, it won't be what messes you up. Now, do you know the next time when sine of an angle equals a half? So the first time is pi 6. Anybody know the second time? So if you think of sine, so here's pi 6, and if you want the same height, because the sine is the y value, it's going to be at the other side, 5 pi 6, which is pi 6, step back pi 6. So that says that our intersections happen at pi 12ths and 5 pi 12ths. So those are our angles. Ooh, this is already looking more interesting than we normally get to see. All right, so we know our angles we start and stop. We know our curves in terms of r. So we're ready for our formula. The area in polar coordinates. 1/2 integral start to stop, which are two angles, alpha, beta. And then we have our outer curve, I'll call it f of theta, squared minus g of theta, squared d theta. So where the f of theta, that's the further curve out, g of theta, that's the closer curve. So in our case, our outer curve is the circle, r equals 2. Our inner curve, good news, we're going to square it, the square root of 2 over sine of 2 theta. So we get 1/2 integral from pi 12ths to 5 pi 12ths, 4 minus 2 over sine squared of 2 theta, d theta. So that's the integral that we're going to need to carry out. All right, well, can we do it? I think we can. All right, how do we do it? Well, what's another way to write 1 over sine squared? Would it just be sinus 2 theta? Oh, you're right. Because we squared it. Thank you. Thank you. What's another way to write 1 over sine? Cosecant. So, if I pull out a 2, just to clean things up, let's get rid of the half. So it gets the integral of pi 12ths to 5 pi 12ths of 2 minus cosecant 2 theta d theta. Now, normally we haven't asked you to memorize the integral of cosecant, but very conveniently for reference, they gave us some information. They gave us a hint. They gave us the integral of cosecant. Of course, they also gave us the integral of cosecant squared to throw us off the scent. Sometimes they give us too much information. It's not that you want to use it. I did that once on a test a long time ago. There was a trig problem. I said, well, here's this identity if you want it. You didn't want it because it made it worse. But students didn't know that. All right. That was back when I was mean. Now I'm mellow. This is mellow, Steve. All right. Well, let's see. So we have the integral pi 12ths, 5 pi 12ths of 2 minus cosecant 2 theta d theta. So this becomes, well, the integral of 2 is 2 theta. That's not hard. The integral of cosecant is minus cosecant cotangent. Now, there's one other thing that we have to do, though, because we have that divide by 2 going on, which is divide by 2. And then we have to evaluate from pi 12ths to 5 pi 12ths. All right. Good news. Minus minus makes plus. So what do we have? We plug in 5 pi 12ths. So we have 2 times 5 pi over 12 plus, am I off? Oh, darn it. Man, I'm off my game today. Okay, we'll just edit that out. No one will know. Don't tell anybody. I'm going to lose my street cred. All right. Okay, let's try it one more time. Cosecant. I was thinking of integrating cotangent, not cosecant. Man. All right. Let's try it again. 2 theta. I got that part right. That's good news. Okay, integral of cosecant is log, with another minus in front, cosecant plus cotangent. There's a 2 on the inside, and divide by 2. Okay, how did I do? Did I get it that time? Whew, good. All right. Evaluate from pi 12ths to 5 pi 12ths. We put the tough ones on the review. The ones on the exam, those are the fun ones. Or is it the other way around? I can't remember. Okay, 2 times 5 pi 12ths minus minus plus 1/2 log of cosecant of 5 pi twice that, so that's 5 pi 6, plus cotangent of 5 pi over 6. Okay. And then we're going to subtract 2 times pi over 12 plus 1/2 log of cosecant pi over 6 plus cotangent of pi over 6. Okay. I'm almost nervous to keep going, but let's keep going. All right. Now that I have an audience here to correct me. 2 times 5 pi 12ths, well, that's 5 pi 6. That's not so bad. And then we're going to subtract pi 6. So that's from these two terms here. So we've gone these terms here. Now, let's think about cosecant of pi 6. That's 1 over sine of pi 6, and we said sine of pi 6, that's the same as, well, it's 1/2. And it's the same, by the way, as cosecant of pi 6. Sorry, whoops, I meant sine of 5 pi 6. So this part is 1/2, and this part, whoops, is 2. And this part is 2. I really should have stopped. All right, now cotangent of pi 6. What's cotangent of pi 6? Well, that's 1 over tangent of pi 6, which is root 3. So this is square root of 3. Cotangent of 5 pi over 6, that's 1 over tangent of 5 pi over 6. And tangent of 5 pi over 6 is minus root 3. So this is minus root 3, and that's plus root 3. So we have plus 1/2 log 2 minus root 3, and then minus 1/2 log 2 plus root 3. All right, that's pretty good. Are you convinced? We can keep simplifying, but it's not really helpful. So we'll stop there. Okay, good. Well, but the important news, it's possible. It's possible. You can do these things. I think those were the 2 hard ones. I promise I'll get the rest. Determine the value b so that the area enclosed by the curve r equals 4 plus b sine 3 theta has area 20 pi. Okay, so what do we need? Well, what does this curve look like? It depends on b. So depending on your choice of b, what you'll get is something that looks a little bit like one of those fidget spinners, if you've ever had one. That's roughly what this looks like. Now, the b will either make it more narrow, coming on the inside, or push it out. So, okay, so what is it? Well, we want to make sure that this area here, we want it to have area 20 pi. So in this case, it's not about finding the area, because we're told the area. It's saying find the right curve with that area. So 20 pi is our area. But our area is also 1/2 integral, and in our case, we're just going to go all the way around, 0 to 2 pi, and our curve is 4 plus b sine 3 theta squared. All right. So what are we going to do? Well, I can move that square across, that 2 across, so that I get 40 pi is integral 0 to 2 pi, and now we square. So 16 plus 4b sine of 3 theta plus b squared sine squared 3 theta. And that's what we're integrating d theta. Now, some of this is straightforward to integrate. So let's see, what's straightforward? The 16, that's pretty straightforward. So, would that be 8b instead of 4? It's going to be 0 in a minute, but yeah. It's 8b for right now. So the 16 is pretty straightforward. The sine 3 theta is pretty straightforward. The sine squared, how do you integrate sine squared? Power reduction. So the integral of sine squared, if you don't integrate sine squared, this becomes 1 minus cosine and double the current angle, so 6 theta over 2. So what we're going to integrate is 16 plus 8b sine of 3 theta plus 1/2 b squared, and then minus 1/2 b squared cosine 6 theta d theta. So we get 16 theta plus, here, the integral of sine, it's actually not plus, it's minus 8/3 b cosine 3 theta plus 1/2 b squared theta. The integral of cosine 6, well, that's going to be 1/12 b squared sine 6 theta. Because you have to, cosine becomes sine, then you have to divide by the 6. So that's where the 12 comes from. And we're going to evaluate from 0 to 2 pi. So we get 32 pi minus 8/3 times b times cosine of 6 pi, which is 1. Plus 1/2 times b squared times 2 pi, which is b squared. Minus 1/12 times b squared times sine of 12 pi, but that's 0. Sine of 12 pi is 0. It's like you went 6 times around. So it's really the same as just saying sine of 0. Subtract, well, 0 minus 8/3 b, because you get cosine of 0 is 1. That'll be 0. That'll be 0. So the 8/3 b's cancel. So you end up with 32 pi plus b squared. And remember, that's equal to 40 pi. Whoops, I forgot to multiply by pi there because it's 2 pi times a half. So 40 pi is 32 pi plus b squared pi. So subtract 32 pi. 8 pi equals b squared times pi. Cancel the pi's. 8 equals b squared. Take the square root. B equals square root of 8. All right. And there you go. Now you might say, could I also have b equals minus square root of 8? Well, yes. It's just going to be a rotation of the figure that you see there. Find the tangent line to the parametrized curve x of t equals t cubed plus t, y of t equals t to the fourth plus 3t squared plus 1 at time t equals 1. All right, this is much simpler. So tangent line says, if I need a tangent line, I need to have a slope, and I need to have a point. So on a parametrized curve, we know the time, so what you do is you plug in that value. So to get the point, that's going to be from x of 1 comma y of 1. So in our case, we plug in 1. 1 cubed plus 1 makes 2. 1 to the fourth plus 3 times 1 squared plus 1, that's 1 plus 3 plus 1 makes 5. So there's our point. Now our slope is rise over run. So that's change in y over change in x. So you get y prime, which is our change in y, over x prime, which is our change in x. So to find our slope, we need to find our derivatives. So y prime of t, we'll do that first because that's the one on the top. Take the derivative, that's 4t cubed plus 6t plus 0. Derivative of 1 is 0. X prime of t, come over and take the derivative of x, 3t squared plus 1. So if I want y prime of t over x prime of t, it's 4t cubed plus 6t over 3t squared plus 1. So plug in 1, because that's where we care about. And in our case, we're going to get 4 plus 6, which is 10, over 3 plus 1, which is 4. So we get 5 halves. So there's our slope, 5 halves, because we really want at 1. So we have our point, we have our slope. So our line becomes y minus the y coordinate is our slope, x minus the x coordinate. In general, y minus y naught is m times x minus x naught. All right. Good. I got that one. Whew, I hope. Okay. So that's sort of the applications phase, which gets us into the last part of our course, which is the fun part. We're into our series phase. So find the sum n equals 1 to infinity of 1 over e to the n minus 1 over e plus 1 to the n. Now you're probably thinking, whoa, wait a second, you can't ask that question because you said telescoping series were off. Is this a telescoping series? No. See, we know what you're looking for, and we know how to make things look like what you're looking for. So pay attention. Read things carefully. So what is this? Well, you see, I have n's in exponents. What I really have, let's break this into two parts. 1 to infinity, 1 over e to the n, minus 1 to infinity, 1 over e plus 1 to the n. These are two geometric sums that we just sort of squished together. Now, how do you find a geometric sum? Well, to find a geometric sum, it's the first term is your numerator over 1 minus r. The r here, this is what you multiply by at each stage. And that's where the word geometric comes from. It's the idea of multiplying. So this first sum, to get the first term, I plug in where I start. So I start at 1. So the first term is 1 over e. Then I divide by 1 minus what I multiply by. That's what's inside the thing to the n. So it's actually still 1 over e again. The second sum, same thing. First term, plug in 1 over e plus 1. Divide by 1 minus 1 over e plus 1. And if we don't have to simplify, we don't simplify. And that's it. That's the answer. So, pay attention. Pay attention. A surprisingly large number of people on the most recent exam struggled with a question very similar to this. So, don't let us fool you twice. Fool you once, okay. Fool you twice, you shouldn't fool people. Wait, no, that's not how it goes. All right. Determine if the series 4 to the n to the power of 4n, divided by n to the 4th times 4n factorial, where we start at 4 and go to infinity, converges or diverges. So this is a very type problem. In fact, it's a foregone conclusion this is going to be fun. Now, it's converge or diverge. So there's no, is it conditionally convergent? There's no, just does it converge or does it diverge? And it says to justify, which says include the name. So we're going to make sure to write down anything that we do. So what do we do? What does this problem tell us we should be doing? There's a clue. It's right here. Now, to catch up with your generation, I should probably shade it the right color. It's now blue. It's factorial. So, when you see factorial, what do you think? It's ratio test. All right, so we're going to use a ratio test. So, ratio test says, look at the limit as n goes to infinity of an plus 1 over an. Now, if you have something that's a negative possible thing in there, like a minus 2 to an n or something, you throw in the absolute values. If you know all your terms are positive, you don't need to worry about absolute values. Ratio test always assumes you're dealing with non-negative expressions. So here, the thing about the ratio test, there's not really any big surprises. You just have to be careful. So when I say be careful, it's at our next stage, where you put in n plus 1. So the idea is everywhere you currently see an n, put in n plus 1. And this is a case where parentheses are your friend. So if anything, put in lots and lots of parentheses so you don't miss anything. So I'm going through, and everywhere where I'm seeing an n, I'm putting in n plus 1. And I'm being extra generous with my parentheses. Don't worry, we can recycle parentheses for later problems. All right. Now that's my an plus 1. I have to divide by an, but it's easier to multiply by the reciprocal. So n to the 4th, 4n factorial, divided by 4 to the n to the power of 4n. Now at this stage, we start looking for ways to break things up. So there's a couple of things we can look for. As an example, this part, 4 to the power n plus 1, that's really 4 to the n times 4. So that's going to be useful because that'll let me cancel a 4 to the n. I have a factorial. I want to cancel the factorials because that's harder to work with. So I'm going to do the other factorial down here. Now, what do I have currently? It's currently 4n plus 4 factorial. So to cancel with the 4n factorial, start pulling off terms. 4n plus 4 times 4n plus 3 times 4n plus 2 times 4n plus 1 times 4n. And they say, oh, wait, 4n, perfect, stop there. So we're pulling off the first 4 terms. And now, if we do that, we're going to be in pretty good shape. Here, let's see, what else do we have? I have n plus 1 to the power of 4n plus 1. I can write this as n plus 1 to the 4n times n plus 1 to the 4. Because I can think of that as 4n plus 4. And so if I do these things, so let me just say I replace things by their corresponding expressions. What do we cancel? The 4 to the n's cancel. N plus 1s to the 4s, they cancel. 4n factorials cancel. Now we have to see what's left. Well, where are we? So we're currently at the limit as n tends to infinity. We have a 4. That hasn't been canceled with anything yet. We have an n to the 4th. And then we have this n plus 1 to the power of 4n. Downstairs, we've got a lot of terms. 4n plus 4 times 4n plus 3 times 4n plus 2 times 4n plus 1, and an n to the power of 4n. Okay, so that's what we currently have. There's two pieces here, so let's look at the two pieces. So this is the limit as n goes to infinity. The first piece is, I'm going to call it your polynomial pieces. So you have 4n to the 4th upstairs, and then all that stuff downstairs. And there's a lot of stuff, but it's all polynomial. 4n plus 3, 4n plus 2, 4n plus 1. Just the polynomial for right now. That's one part. Then you have this other part. n plus 1 to the 4n over n to the 4n. Now, let's think about what's the best way to write that to help us go forward. So n plus 1 to the 4n over n to the 4n. Well, they both are to the 4n power, so I can write that as n plus 1 over n to the 4n. Now at this point, we say, okay, what's an even better way to write that? And here's the answer. The better way to write it is n plus 1 over n to the n to the 4th power. Now why? Little side note, there's a limit you should know. There's actually two that you should know. Here's the first one, n to the power of 1 over n, that's 1. The second one that you should know is n plus 1 over n to the power n is e. So, when you see this particular thing, n to an n, at some point an e is going to pop out. It's unavoidable. It's going to happen. So if you see that n to the n, there's an e coming. Be prepared for it and be on the lookout. So now we think about what happens. Well, from what we just wrote down, this inside part is going to go to e, but then there's to the 4th power. So don't forget about that, because I'm probably going to forget about that in a second. Let's look at what's over here. So we have a 4, n to the 4th, and then we have a lot of stuff downstairs. Now, at this point, it's a polynomial over a polynomial. You look at your degrees. What's the power on the top? N to the 4th. What's the power in the denominator? It's n to the 4th. So you look at your leading coefficients. So it goes to your leading coefficients. The leading coefficient on the top is 4. What's the leading coefficient downstairs? Well, 4 times 4 times 4 times 4. 64. So, what do we get? Oh, wait. That's not enough 4s. Times another 4. Okay, now is that enough 4s? Yes. Well, I mean, it's an appropriate question. After all, I think it is, if I recall, a special day today. It is May the 4, as they say. May the 4 be with you? No? All right. All right. Anyways, so we end up with our limit. The 4's cancel. We got this e to the power 4 over 64. Oh, good. Now, what's left for us to decide? Yeah. Is this smaller than 1 or less than 1? That's the question. Well, it turns out that e to the 4th is less than 60. Now, had this been a test, we would have told you that. But since it's just a bunch of friends casually doing math together, it's okay for us to not tell that. So what can we say about e to the 4th over 64? Well, it's less than 1. So, the limit as n goes to infinity of an plus 1 over an is something that's less than 1. Well, if it's less than 1, what's the conclusion? Yeah, this converges. If something is smaller than 1, it will converge. All right. Good. Determine if the following series converges or diverges. Now, justify. Include the name of any test used. Now, it just looks like a mess. Now, but that's okay. When you see stuff that looks like a mess, well, what I like to say is there's a lot of noise. Now, how do you handle the noise? The key is you get rid of everything except the most important term. So, but what allows us to do that? So we need to justify that. So here we go. So by limit comparison test, only need to look at the highest growth terms. So we're going to go through and only look at the highest growth terms. So that's what the limit comparison test allows you to do. So if you see something with a lot of noise, just say, I'm applying the limit comparison test. I only need to look at the terms that grow the fastest. Everything that grows slower, I ignore. So let's go through and see what we get. So we're going to compare it to, in limit comparison test, let's see here. So we have to go through any set of parentheses. So upstairs we have a nice set of parentheses, and we pick out the highest growing thing. So our choices right now are n to the 7th, 17n squared, log of n, and 7. Which one grows the fastest? N to the 7th. That's the one we keep. Now we go to our next set of parentheses. So that's that set of parentheses there. And I have log n versus log n. Well, which grows faster, log n or log n? Log n. So that says I throw away the log. So log n. Now, be careful here, because there's that 2. Means I'm going to square that. Come to our next set of parentheses. Now I got to pick. I have 3 terms. 3n to the 8th, cosine n to the 12th, and negative 1 to the n. Now, there's lots of interesting choices here. That's an exponential term. So exponential grows pretty fast, right? Not always. In fact, this doesn't really grow at all. It's always 1 or negative 1, so it's not that. So, okay, probably one of these two. I see a 12th. That's pretty promising. Is that the largest term? No. It's a red herring because it's inside a cosine. It doesn't matter how big that part grows. Once you put a cosine in front, it's not going to be big. So what is it? Yeah, 3n to the 8th. All right. So that's our limit comparison test says. I just need to look at that. The question about whether it converges or diverges is this question. Well, the constant, I can pull that out, 1/3 sum from 5 to infinity of 1 over n log n squared. Does that converge or diverge? Well, that's it's tricky. It's tricky. Because this power 1 over n, if it was a p series, it's like right near the edge. Because 1 over n, the sum of that diverges, but just barely, just barely. And oh, I forgot to put the n here. There's an n there. Log n squared. Okay, so we can't use a p-series test because it's not a p-series. What test do we use? Well, the answer is, now we use an integral test. Now you might say, why? Well, because there's not an obvious thing to compare it to. We've already used up limit comparison. Essentially, the only thing limit comparison is just ignore the noise. That's what limit comparison is for. So we've already used it. We're not going to be able to really use it again. This is not the root test, the ratio test will go to 1. They're going to be inconclusive. So integral test. 5 to infinity of 1 over x log x squared dx. Well, can we integrate this? We can, because if you let u equal log x, you get du equals 1 over x dx. So this becomes the integral log of 5 to infinity, because I'm still going to go to infinity. As x goes to infinity, log tends to infinity. What do we get? We get u squared downstairs, and then the 1 over x dx becomes du. So u to the minus 2 du. And what is that integral? It's minus 1 over u. Evaluate from log 5 to infinity. And we evaluate, of course, when we say we evaluate at infinity, it means we say what happens as we go towards infinity. If they don't tell us you have to justify it, then we know how to do it. If they tell us to put the limits in, we'd put the limits in. But here, they didn't tell us to put limits in, so we're good. 0 minus 1 over log 5. But I really don't care about the number. What I care about is that it converged. Okay, so the integral converged. What's our conclusion? Well, the integral test says whatever the integral does, in terms of converging or diverging, the sum does. And so, since the integral converged, this implies that the sum converged. Now, in particular, this sum converges, but by the limit comparison test, we already know that whatever this sum does, the original sum does. So our conclusion is it's another converging one. All right. Well, that's good. Okay. Find the second order Taylor polynomial for f of x equals the square root of e to the x plus x centered at x equals 0. So, okay. So we need to find a Taylor polynomial. Now, how do you find Taylor polynomials? So, in particular, second order, well, you look at your center. So in our case, our center is at 0. So it's f of 0 plus f prime of 0 times x minus 0 over 1 factorial plus f double prime of 0 times x minus 0 squared over 2 factorial. And we stop. Second order says just go up through the second derivative. You don't have to go any further. So what we need to do is we need to find these terms, f of 0, f prime of 0, f double prime of 0. So it looks like we have a lot of fun differentiating ahead of ours. So e to the x plus x to the half. That's our function. F prime of 0, do the chain rule, 1 half, e to the x plus x to the minus 1 half times the derivative of the inside, which is e to the x plus 1. Well, okay, it is what it is. And I don't see really any good simplification. So we're just going to, whoops, I put 0. That's x. Sorry, getting ahead of myself. We're going to evaluate that in a minute. Second derivative. All right, we're going to do product rule. So 1 half times minus 1 half times e to the x plus x to the minus 3 halves times e to the x plus 1. So that's the derivative of the first term times the second term, plus, now I take the first term, e to the x plus x to the minus 1 half, times the derivative of the second term, which is e to the x. So there's our function, our derivative, and our second derivative. Now, some people forget to evaluate, and they say, oh, okay, I'm going to put that in there, I'm going to put that in there, and I'm going to put that in there, and like, oh my gosh, they didn't give me enough space on my paper to do all that. No, we gave you plenty of space if you do it right. So pro tip, do it correctly. All right, so plug in 0. E to the 0 plus 0 is 1. So 1 to any power is 1. All right, so that's f of 0. F prime of 0, well, we're going to get a half. Then e to 0 plus 0 is 1 still. 1 to any power is 1 times e to 0 plus 1. Which is 2. So 1 half times 2, which is 1. Oh, well, that was kind of nice. Then f double prime of 0 is going to be 1 half times negative a half. So let's see, that's negative 1/4. E to the 0 plus 0 is 1 to the minus 3 halves. Well, that's going to be 1 to the minus 3 halves. Okay, so that's 1. E to the 0 plus 1. Well, 1 plus 1 is 2. And then another 2, so 2 times 2 makes 4. Plus 1 half I'll have e to the 0 plus 0, which is 1 to the minus 1/2, which is 1, times e to the 0. So what does that become? So that becomes minus 1/4 times a fourth is minus 1 plus a half, which is minus a half. So these are the numbers, the 1, 1, minus a half, that go into these slots. So our answer will be 1 plus 1 over 1 factorial, which is 1, times x, so plus x. Then minus a half over 2 factorial. 2 factorial is 2, so you get minus 1/4, and then x squared. And there's our second order Taylor polynomial. Now, on a side note, the second order Taylor polynomial does not have to have an x squared term. It is possible that your second derivative evaluates to 0. You should double check if it does, but it's possible. It's possible. Find the Taylor series for f of x equals 1 over x squared minus 2x, centered at x equals 1. Okay, so this is a nice find your Taylor series type question. So how do we do this? Well, oftentimes you can either do one of two things. You can say, let me go back to the definition. So what is the definition of a Taylor series? So the definition is says you take the sum from 0 to infinity of the nth derivative evaluated at your center point. So, well, in our case, 1 over n factorial x minus 1 to the n. So the definition would say, oh, just take all the derivatives and evaluate at 1. But odds are pretty good that a lot of times your derivatives look terrible. Now, if your derivatives look nice, this is a great option. But if they don't look nice, we should think of other ways. So if we don't do the definition, the other approach is to say, let's adapt. So in other words, adapt something we know. So we think and say, okay, what does this remind us of? And it should remind us of our geometric. So geometric sums look like 1 over 1 minus something is equal to the summation of something to the n. Now, here I'm being very, very big. I'm just saying that 1 over 1 minus whatever I have is whatever I have to the n. So this becomes the age-old question, what's in the box? So in other words, what goes in here, I put that in there. So, all right, how do we do that? So we want to make it look like this. So with that in mind, we start thinking about x squared minus 2x. Now x squared minus 2x, and we're told that x equals 1. And that should like ring a bell, because we've seen x squared minus 2x before. Another way to think of x squared minus 2x is as x squared minus 2x plus 1. Now, why do I bring this up? Well, x squared minus 2x plus 1 turns out to be x minus 1 squared. Now, that's really useful because I want things to look like x minus 1s to powers. So if I see x minus 1s, I'm like, yes, success. However, that's not the problem I was given because there wasn't a plus 1. Well, subtract 1. It's our age-old add and subtract. So, what's another way for us to write this? So we get 1 over x minus 1 squared minus 1. Now, it's not quite our form, but we can do the following trick, which is called put a negative in front. Pull the negative out. And if you do that, then we're like, perfect. Perfect. So, I have 1 over 1 minus something. That's my box. That's what goes into the box. So this becomes minus summation n equals 0 to infinity of x minus 1 squared to the n. Now if I want, I can put the minus inside or I can leave it out. That will be okay, either one. So I'll put it inside. And here, x minus 1 squared to the n becomes x minus 1 to the 2n power. And there we go. We've now written our Taylor series. Now you might say, how do you know that's the Taylor series? It's just a series. And the answer is, if it's a series, there's only one. So if there is a Taylor series and you find a series, that's the Taylor series. Okay, so that one's not so bad. let's look at another problem. Find the Taylor series for f of x equals 1 over x squared minus 2x, centered at x equals 3. Now, that's a little different here. Not at 1, but at 3. Well, will that have an effect? The answer will surprise you. Or maybe it won't. The problem is we can't do our same trick again, because this doesn't look like x minus 3 squared. So that's the sad news. But the good news is we can still work with it. We're still going to try to adapt. So how do we do it? Well, in this case, what we can do is we can say x squared minus 2x is the same as x times x minus 2. And we're going to pull this apart. So, what does that mean? A over x plus b over x minus 2. And we clear our denominators. You get 1 is equal to a times x minus 2 plus b times x. And you make good choices. Good life choices help you out. For example, choosing x equals 0, well, that will tell us that 1 is equal to negative 2a, or that a equals negative 1/2. And if you choose x equals 2, well, that will tell you that 1 is equal to 2b, which tells you that b is equal to positive 1/2. Now, at this point, you might say, whoa, wait a second, you said there was no partial fractions. We said there was no integration by partial fractions. Partial fractions is an algebra thing. What? You're booing algebra? How dare you? I can't believe that. But we're not going to expect anything very complicated. This is be as sophisticated as we'd expect you to be able to do. So minus 1/2 over x and plus 1/2 over x minus 2. Okay, so there we go. Now, what do? Well, we want these to look like x minus 3s. So we do what we would do if we want things to look like x minus 3s, is we put x minus 3s. I'll bring the half down. So 1/2, 1. I'm going to have x minus 3. But if I subtract 3, I need to add 3. Because I still want to have x. Plus 1/2. And here I'll still have x minus 3. But now the good news is I need to get to x minus 2. So that leaves me with plus 1. Our goal is still the same. We're still heading to the point where we can adapt our geometric sum. So we're getting close. So how do we get there? Well, in our first term, I want this 3 to become a 1. That's easy enough to do. Pull out a factor of 3. So I'll get a 1/6. And then I'd like it to be in front. 1 plus x minus 3 over 3. So I pulled out a 3. Here, I'm already happy with the 1, so I don't need to pull anything out, but I will switch the order. There's one other thing, though. If we look closely at our mold, I'll put it back up here, 1 over 1 minus something. Right now we have 1 over 1 plus something. But again, that's easy enough to fix. Well, how do you fix it? You do 1 over 1 minus x minus 3 over 3. Plus 1 over 2 times 1 over 1 minus x minus 3. So if you have a plus, minus fixes it. So minus 1/6. Now we're in the mold. Summation 0 to infinity of minus x minus 3 over 3 to the n plus 1/2 summation n equals 0 to infinity of minus x minus 3 to the n. And in some sense, that's pretty good. I'd like to go one step further here, which is to say, let's put it into a single sum. Both of them have x minus 3 to the n. And they both start at 0, so it's really easy to just sort of push everything into one sum. And so if you do that, you'll get a single sum, n equals 0 to infinity. And what do we have? Well, they both have minus 1s to the n, because they both have minus there. We also have x minus 3 to the n. So let's just put that at the end. Minus 1 to the n, x minus 3 to the n. Then what's left? Well, we have minus 1/6 And then here, there's a 3 to the n. So minus 1 over 6 times 3 to the n. And then plus 1/2. So I'm grabbing the minus 1/6 and the 3 to the n, and I'm grabbing the half, and there we go. There's our nice Taylor series. And so we can now use this, if we wanted to compute all sorts of fun things, like the millionth derivative at 3. Easy to do now. All right. Well, here we go. Write x to the fourth minus 2x squared plus 2 times e to the x squared as a Taylor series centered at x equals 0 in as simple as possible form. In particular, no power of x appears more than once. That's what simple means. So we can't write a bunch of individual sums. It's got to be sort of like 1. And it actually gave us a hint. Hint, look at f prime of x. Okay, well, there are sort of two things to do. Now, first off, we see this e here, and the good news is we're centered at x equals 0. So we think about the form for e. So e to something is the summation from n equals 0 to infinity of something to the n over n factorial. So that's the form. So whenever I see the e, I know how to adopt the Taylor series for e. All right, so there we go. And the question, of course, is what's the right thing? What goes into our box here? Now, I have two approaches. One approach is I could distribute this out, and then I could do 3 sums, and then I could try to somehow spend the next 20, 30 minutes trying to make those 3 sums into 1 sum. I don't want to do that, because I believe that they wouldn't give us a hint unless it was a useful hint. So let's follow the hint. Let's go down that rabbit hole. F prime of x. So, to take the derivative, we take the derivative of the first term, 4x cubed minus 4x times the second, ex squared, plus the first term, x to the fourth minus 2x squared plus 2, times e to the x squared times 2x, because I have to use the chain rule when I take the derivative of the second term. Now, at this point, I sort of say, I wonder why they asked us to do that. Well, let's explore a little bit more. If we continue our exploration, well, they both have e to the x squared, so we'll pull those out. The first term, I get 4x cubed minus 4x. From the next term, I'm going to get 2x times x to the fourth, which is 2x to the fifth. Then I'm going to get 2x times minus 2x squared, that's minus 4x to the third. Then 2 times 2x is plus 4x. OMG. This is good. The 4x cubes cancel and the 4x's cancel. It's just a single thing. There's no more addition. That was a good hint. Okay, so we're down to just one thing to rule them all, one thing to find them, one thing to bring them all, and in Taylor series bind them. Okay, so the 2x to the fifth, that's good to go as is because it's polynomial. Taylor series are just polynomials. If you have something polynomial, it's okay for right now. The e to the x squared, we've got to make that into our polynomial. That's how we used our form. So that becomes a summation 0 to infinity. In our case, it's x squared goes in the box. So x squared to the n over n factorial. Now, clean this up a little bit. We'll put the 2x to the fifth inside. So summation n equals 0 to infinity. So x squared to the n is x to the 2n. Then I have 5 more, so plus 5. And then I had the 2 in the front, so 2 over n factorial. And now I'm feeling good about myself, except that's not f. That's f prime. So, but that's not so bad. I just have to get to f. So, what's f? You integrate. And the nice thing about series is you just integrate term by term. So that would become 2. X, I add 1 to the exponent, which makes that n plus 6. and I divide by that exponent, n plus 6, n factorial. Okay, is that my answer? No, because I've omitted something. I have forgotten one crucial thing about integration. Plus c. Okay, well, oftentimes the c we can ignore. Is this one of those times? Well, to figure it out, I got to solve for c. So how do I solve for c? We need to choose. Choose an x. What's a good x to choose? 0 is a great x. So we plug in x equals 0. Plug in 0. 0, 0, 2 times e to the 0. So f of 0 is 2. Plug in 0 here. Everything drops out except the c. So, good thing we checked for that constant, otherwise we would have lost a point. Now, one other thing is we can clean up the inside. There's 2 over 2n plus 6. I can divide the 2 downstairs, and I can replace it by n plus 3 downstairs. So our final answer is the summation 0 to infinity x to the power 2n plus 6 divided by n plus 3 times n factorial, and the plus 2 can be on the outside because that's the only constant term, and we're done. And we really are done because look, no more.